Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, good night everyone. So in this session, you are going to learn how to analyze trust structures using stiffness matrix method. Okay, so stiffness method is actually second topic under course indeterminate structures CES521. So under this topic, you are going to learn how to analyze. Number one is truss. Truss. Number two is beam, and number three is frame. Start with truss, followed by beam, and last one is frame. Frame structure. So we will use stiffness method. Okay. So let's start now. So our focus for tonight is to understand the term that we will use under the stiffness method, because stiffness method is actually one of the structure that can be used to analyze not only indeterminate structure but also determinate structure. So one of advantages of using stiffness method is actually we can use it to analyze both determinate and indeterminate structures. So before that, we have to actually understand several terms under stiffness method. Maybe the new term for you to understand, and before we continue to get the final learning outcome, which is calculating deflection or displacement, and then calculate reaction, and then we calculate we calculate internal forces. We have to understand about what is stiffness, what is element stiffness matrices, what is structure stiffness matrix. Okay. So let's look at the learning outcome first. So by completing this chapter, you should be able to, number one, okay, the learning outcome. Okay, always bear in mind the learning outcome is very, very important. Means that at the end of this topic, you should understand, you should be able to analyze structures using stiffness method. So you have to, number one, you have to be able to identify constraint and unconstrained degree of freedom. Okay, the special term here that we will use regularly under stiffness method is called as degree of freedom. So you have to know what is actually degree of freedom. In the textbook, degree of freedom actually means displacement component. So there are two degree of freedom, two displacement component in truss per node. There are two also in beam per node, and there are three displacement component in frame per node. Okay, so you will learn about understanding what is degree of freedom. And degree of freedom is we have to divide into two terms. It is constrained degree of freedom, and unconstrained degree of freedom. Constrained and unconstrained degree of freedom. So you have to understand about what is constrained degree of freedom, what is unconstrained degree of freedom, because this is very important. Understanding degree of freedom, you can actually apply the same principle, the same concept for not only for truss but also in beam as well as in frame analysis. So we will go quite detail in the concept of degree of freedom under truss structure, so that whenever we move to beam and frame, you will understand how to use the degree of freedom for beam and frame as well. Okay, so next learning outcome is from degree of freedom, we will actually establish the element stiffness matrix. element. The keyword here is stiffness, the stiffness factor, stiffness matrix. We call this in stiffness method. All solution we will use matrix calculation. Okay, matrix calculation, matrix multiplication. Okay, so all terms we will have to produce in matrix form. So that is why the second learning outcome is you have to be able to formulate element stiffness matrix. Element stiffness matrix. As I mentioned in class today, as we mentioned in class today, we have to okay okay element. Okay, element refers to member. Element refers to member. Element. Okay, the special term that we use in stiffness method. Stiffness method is element refers to member. So conventionally we call as member AB, member BC, member CD, but now we will use the term element to represent member. And element we use numbering. So we will call member as element number 1, element 2, element 3, and so on. Element. Okay, and then join. Remember, join. We will use the term nodes to represent join. Nodes. Join A, join B, join C. We change to node. Okay, we will call as node number. We will call as node number 1, node number 2, node number 3, and so on. Okay, understanding node is very important because degree of freedom we will count per node. Degree of freedom we will count per node. The degree of freedom we will call per node. Okay, for the degree of freedom we will count per node. Okay, next, from the element stiffness matrix, actually we have to combine to have what we call a structure stiffness matrix. We combine to have the structure stiffness matrix because structure is come from combination of element. Structure, one truss structure or one beam structure or one frame structure is actually come from combination of many elements. So, so at the end of this topic, you should be able to produce the structure stiffness matrix, and we get the structure stiffness matrix from combination of many element. Combination of many element. Okay. Actually, that is the aim for this session. We will try to understand and we will try to understand and establish element stiffness matrix and structure stiffness matrix first before we move to the last outcome. The last outcome is the stiffness equation, what we call as stiffness equation. If flexibility method, we have flexibility equation, and flexibility equation is compatibility equation. In stiffness method, we have stiffness equation, and stiffness equation is actually force displacement equation. Force displacement equation. This is very important because by solving the force displacement equation or the stiffness equation, we will solve for the displacement and forces. We will solve for displacement and forces. Okay, so the basic thing that you have to understand is the stiffness matrix, the element stiffness matrix, and the structure stiffness matrix. That is very, very important. We will have to produce the structure stiffness matrix, and it must be correct. Because if you produce the wrong stiffness matrix, you will get a wrong displacement and wrong forces. So we have to make sure that we produce the right stiffness matrix. The right stiffness matrix. Okay, so an indeterminate structure using stiffness matrix. So we will analyze truss, beam as well as frame. Okay, so advantages of stiffness method. Advantages of stiffness method. I have said just now, stiffness method is special because we can use this method to analyze both determinate and indeterminate structures. Stiffness method can be used to solve both statically determinate and indeterminate structures. Uh, if we try to compare this method with flexibility method, it is actually two different method with different procedure, but the outcome is actually same because we actually analyzing reaction from displacement that we will get from the stiffness equation. We will solve the reaction. Okay, number two advantage number two, using stiffness method we will yield the displacement and forces directly. We will yield displacement and forces directly. We will, by solving stiffness equation or force displacement equation, we solve displacement first. We will solve displacement first, and displacement will occur in unconstrained system. Unconstrained, okay, unconstrained degree of freedom. Unconstrained degree of freedom. And after that, we will use the displacement to solve reaction at the support. Reaction at the support as well as member forces in truss, reaction forces. And we use the displacement to calculate forces. And reaction at the support is actually located in constrained system. Reaction at the support actually occur in constrained system. So what's the difference between unconstrained and constrained? Constraint refers to support. Constraint refers to support. Okay, I repeat again, constraint refers to support. So at support, there are unknown reaction. Okay, that is objective. That is advantage number two. Another advantage of using stiffness method. Okay, this stiffness method is the theory behind computer operation, behind structural engineering software. This is the theory behind it. So that is why the process later on is quite easy comparing to flexibility method. The stiffness method is actually very easy to formulate. Okay, because we will produce all in matrices. Size of the matrix will be depending on the degree of freedom for element. Okay, so we have to understand the fundamental of stiffness method first before we move further. Okay, so you have to imagine like this. We will analyze structure. For example, the structure is truss. We will analyze structure. So one truss is a structure. Truss is structure. Okay, and truss has combination of many elements. Truss has combination of many elements. So, in order to produce the structure stiffness matrix K, in order to produce the structure stiffness matrix K, we have to divide the structure into element. We have to divide the structure into element. So we have one structure. Structure is combination of many elements. So in order to produce one stiffness matrix, we call it a structure stiffness matrix. We have to produce element stiffness matrix first. Element stiffness matrix, then we produce structure stiffness matrix. Element producing structure, many element producing structure. So when the question is a truss is a structure. So what we need to do is we have to divide the structure that we get into element. we have to divide the structure into element. Divide into element 1, element 2, element 3, depending on the structure. Okay, so the concept is the structure, we have to divide the structure into a series of finite discrete elements. So just focus on the word element, and identifying their endpoint as node. So one element consists of two nodes. One element, one node we cannot call as element. One element is actually combination of two nodes. One element, two nodes. One node, combine two node, we have one element. Combine two node, we have one element. And combining many element, we have structure. So it will be started from one nodes. Combine two nodes become element. Combine many element become structure. So we have to look backward. Structure, element, nodes. Structure, element, nodes. Okay, structure, element, nodes. So we will produce what we call as element stiffness matrix. We will produce what we call as element stiffness matrix, means stiffness matrix for each element. So the symbol is small letter of K. If we have three element, we have K1, K2, K3, K1, K2, K3. And structure stiffness matrix, the symbol is capital K. So K is equal to K1 plus K2 plus K3. Combination. From nodes become element. Many element become structure. Two node become one element. Combining many element become structure. So we are producing the structure stiffness matrix. Okay. The unknown displacement. So after producing the element stiffness matrix, we combine to have the structure stiffness matrix. And after that, what we need to do, we have to apply stiffness equation. Stiffness equation is Q is equal to KD. Q is forces. K is stiffness matrix. D is displacement. Q is equal to KD. Okay, so by having this, we can actually solve the equation and solve for the unknown displacement. And after that, we will produce the forces reaction at the support. And in TRUSS, we can continue to calculate member forces. Okay, please read again in the textbook. So all this actually I get from the textbook. Okay, please read about the what is stiffness matrix, element stiffness matrix, structure stiffness matrix, and stiffness equation. What is stiffness equation? Stiffness equation, and then from the stiffness equation, we will produce the we will solve displacement, and after displacement is reaction at the support. Okay, so this is basically the procedure. We have to do preliminary preparation for analysis. So there are some important thing that you need to understand, including understanding degree of freedom. So you have to, after that, we have to establish element stiffness matrices K, small letter of K, and then the structure stiffness matrix, capital letter of K. And then the equation, the stiffness equation, Q is equal to KD. Q is equal to KD. Okay, and then we determine unknown displacement, then only unknown displacement, unknown reaction, and member forces. Okay. If you have any question regarding this, you can write in chat box, yeah, in chat box. Okay, so this is actually the coverage of stiffness matrix, because stiffness matrix, as I mentioned, it covers 3 types of structure under CES521. Number 1 is trusses, number 2 is beams, number 3 is frame. Okay, so the keyword that you have to understand is degree of freedom. Degree of freedom. Okay, so as you can see in screen right now for trust, okay, trust has 2 degree of freedom in X and Y component. Trust has 2 degree of freedom in X and Y component. Okay, look at beam. Beam has also 2 degree of freedom in Y and Z component, and frame has 3 degree of freedom per in X, Y, and Z component. So after this, we will look into quite detail into trust analysis and try to understand what is 2 degree of freedom in X and Y component after this. Okay. Okay, we take a break about 1 or 2 minutes before we continue to the next section, analysis of trust. Okay, let's continue. So we focus on trust analysis. Okay, the learning outcome that I have mentioned just now. Okay, you should be able to identify unconstrained and constrained degree of freedom for trust. Unconstrained, look at the word unconstrained and constrained degree of freedom. Unconstrained and constrained degree of freedom. Okay, what does it mean? Constraint refers to support. Constraint refers to support. Okay, constraint refers to support. So I actually have put the textbook into your OneNote. Into your OneNote, I have put the ebook. Okay, in the textbook, stiffness method is under three main topic. Topic number 14 for truss structure, topic number 15 for beam structure, and topic number 16 for frame structure. Okay, so let's look at the truss structure first. Okay, about the degree of freedom in truss structure. Okay. Okay, just ignore about the unit used. So we just need to focus on the truss itself. Okay, this is a truss. This is a truss. Okay, this truss has 1, 2, 3. Okay, so looking into the truss, there are two pin support. There are two pin support. And another one two pin support at node number 1 and node number 3. Remember, as I said just now, we will use node number, node N-O-D-E, node number. We will use node number, node, okay, node to represent join. So we have, by looking into this, we have node number 1, okay, node number 2, and node number 3. Okay, note number. If you are given one truss without having any note number, you have to put the note number. That is the first thing you need to do when we want to analyze truss structure. Okay, so by looking into this, there are three joint actually, and we call joint as node. So there are three nodes. Note number 1, note number 2, and note number 3. Three notes. Okay, and note because we use in numbering, element also we will use in numbering. So we will normally write note number into circle like this. Okay, note number 1 we write like this in the diagram. Note number 2, we write like this. Note number 3 we write like this. Okay, it is notes. Okay, so looking into this, there are three notes. Okay, three notes means three joint. Okay, we don't call as joint A, joint B, joint C, but we call as note number 1, note number 2, and note number 3. Okay, so from note we will producing the what we call as element. Okay, note produce element. An element is member. Member AB, member BC, member AB, member BC. Okay, member AB, member BC. So looking into diagram A, so we have note number 1, note number 2, note number 3. Okay, so we just need to label the element. If the element name, if element number is not given, we have to put the element name. So we have to put the element name. We just put number in element, and number in element we put under the box. Okay, so element number 1, element number 2. Remember, one element we get from two nodes. This is element. Okay, N and F refers to nodes. N and F refers to node. Okay, near N is refers to near N, F is refers to far N. So all the term we use here is actually based on the coordinate system, because when we transform this into the software, So this is all the term that is used in the software. Okay, N refers to near N, F refers to far N. Okay, means that one element actually come from combination of two nodes. Near N node and far N node. Near N node and far N node. That is element. And combination of many element producing structure. Combination of many, more than one element. When we have more than one element like this, we have combination of element 1 and element 2, combination of element 1 and element 2 producing structure. And this structure is truss structure. This structure is truss structure. Okay, so there are two element. There are two element. We have element 1. We have element 1 combining node number 2 and node number 3. We have element 1 combining node number 2 and node number 3, and we have element 2 combining node number 2 and node number 1. We have node number 2 combining node number, we have element number 2 combining node number 2 and node number 1. So we have two elements. We have two elements. So combine 1 and 2, we produce a truss. We produce a truss. Okay. There are two pin support. There are two pin support which is located at node number 1 and node number 3. There are two pin support that is located at node number 1 and at node number 3. Okay, so now we will try to understand what is degree of freedom. Degree of freedom. Degree of freedom. And degree of freedom, always we have to divide into two terms. The degree of freedom, we call it as unconstrained. Unconstrained. We call it as unconstrained. Unconstrained degree of freedom and constrained degree of freedom. Okay, this one, make sure you understand it very, very well. This is the first step to do before we continue to the other step. Okay, so degree of freedom we will label at node. Degree of freedom we will apply at node. Okay, and in truss structure, there are two degree of freedom. There are two degree of freedom in X and Y component. In X and Y component, what does it mean? What does it mean, X and Y component? So this X and Y is actually the degree of freedom. This X and Y component. Okay, and degree of freedom, you have to relate with forces and displacement. Degree of freedom, we have to relate to forces. We have to relate to forces Q and displacement D. Degree of freedom, we have to relate to Q and D. Q and D. Q is forces, D is displacement. Forces Q, D displacement. And in matrix form, the Q is called as nodal forces. Q is called as nodal forces. Okay, nodal is come from the word node. Nodal come from the word node. So Q in stiffness matrix, okay, we call as nodal forces. And D is called as nodal displacement. Nodal displacement. D is called as nodal displacement. Okay, why we put the word nodal forces and nodal displacement? It is because by using stiffness method, we will only determine forces and displacement at nodes. Okay, at nodes. We will determine forces at node we will determine forces at node number 1 and 3. We will determine the forces at node number 1, 2 and 3, and we will determine displacement in node number 1, node number 2 and node number 3. Forces and displacement, we call it as nodal forces. Nodal forces. So every time degree of freedom actually refers to forces, refers to displacement. In simple word, to understand degree of freedom, okay, just imagine like this. Okay, it is displacement component. Displacement component. Okay, so the thrust conventionally. Okay, try to look at this thrust in conventional way. Try to look at this thrust in conventional way. Let's say this is the thrust. This is A, B, C. Conventional way. Okay, this is 100 kilonewton, for example. Okay, this thrust, when we want to analyze the reaction at the support, for example, this is determinate thrust. Okay, so basically we will start with determinate thrust, then although we continue with analysis of indeterminate thrust. So we try to understand about thrust analysis using stiffness method by using the simple determinate thrust first. Okay, so this thrust conventionally we draw like this. We draw the thrust. We put the joint name A, B, C. So we have two members, member AB and member BC, and the thrust is subjected to point load at B, for example. So looking into this thrust conventionally, the next step after this is we have to draw, or we have to put the reaction at the support. That is the free body diagram. The free body diagram, the reaction at the support. Reaction at the support. Reaction at the support. We have two support A and support C. Support A and support C. Normally, we put like this. Okay. Whenever we analyze this using conventional way, we just need to put in any direction that we like. Okay, you can put like this. You can also put in the other way around, or you want to put like this, because it is based on assumption. But you cannot do that in stiffness method, because stiffness method has what we call this, the degree of freedom. Okay, the degree of freedom in X and Y component, and we have to use the degree of freedom in this component of the direction of component. Okay, we have to put degree of freedom in this X and Y direction. We cannot change the direction. Okay, if we analyze the thrust using previous understanding, when we draw the free body diagram, we can put the reaction, because it is based on assumption. Then we apply equilibrium equation, but we cannot do that into this one. Okay, because we have to refer to the sign convention in stiffness method, and sign convention in stiffness method always refers to this X and Y component. Refers to X and Y component. X and Y. X and Y. This pair. X and Y. This pair. And we cannot change this direction. We cannot change this direction. Okay. So we must follow that X direction and Y direction. Okay. So looking into the thrust conventionally, we have so conventional, so we just put in any direction that we like, doesn't matter. Or you want to draw like this, just to identify number of unknown reaction. Okay, we draw this like this. We draw the reaction at the pin support like this. Just for the purpose of identifying number of reaction. Okay, so there are four unknown reaction. There are four unknown reaction. Okay, we count from this. It is pin. Pin has 2 and another pin has another 2. So total unknown reaction in this truss is 4. Total unknown reaction in this truss is 4. 4 unknown reaction. And this 4 unknown reaction in stiffness method, we call as 4 degree of freedom. 4 degree of freedom in constraint system. So reaction at the support, looking into this, there are 4 unknown reaction. So what does it mean? In stiffness method term, 4 unknown reaction means there are 4 degree of freedom in constraint system. Because constraint refers to support. The word constraint is actually refers to support, and constraint also refers to support. At support, displacement is 0. Okay, that is the meaning of constraint degree of freedom system. Because logically, at support, there is no displacement. Because support means no movement. No movement means this in terms of displacement will be equal to 0. So constraint degree of freedom refers to support. Okay, and at support, displacement is equal to 0. Okay, I hope you get what I mean. Try to understand, think, and try to understand. You cannot remember. You have to understand. Okay, you have to understand. You cannot remember. Okay, so we have conventional like this. So why we have to compare to conventional? Because we want to identify number of unknown reaction. And from that, 4 unknown reaction refers to 4 degree of freedom in constraint system. What is the meaning of constraint? Constraints means support, and at support, displacement is 0. Okay. So in this case, in constraint, we have 4. Okay, in constraint, we have 4. For what? 4 degree of freedom in constraint. Because one node have 2 degree of freedom. One node, this x and y is actually degree of freedom per node. We have to put this xy at node 1, xy at node 2, xy at node 3. So at node 1, there are 2. At node 2, there are 2. At node 3, there are 2. So in total, there are 6 degree of freedom. 6 degree of freedom. So in total, there are 6 degree of freedom. Okay. So degree of freedom, we have to apply per node. Degree of freedom, we have to apply per node. Means that each node has 2 degree of freedom in x and y direction. Degree of freedom in x and y direction. And this x and y direction is the sign convention, and everybody have to follow to this sign convention. You cannot change this. You cannot assume sign convention in stiffness method. We have to follow this sign convention, x and y. So this x and y, okay, this x and y, Okay, there are two degree of freedom in X and Y at node number 1, at node number 2, at node number 3. Means that if there are three nodes, if there are three nodes, okay, 1, 2, and 3, degree of freedom in total is 3 times 2. So we should get 6 degree of freedom. 6 degree of freedom. In total, 6 degree of freedom. And this 6 degree of freedom, we have to divide into 2. We have to divide into unconstrained and constrained. Unconstrained and constrained. However, we will normally identify number of constraint, number of degree of freedom in constraint system first, because constraint refers to support. So we can identify number of unknown reaction, right? Number of unknown reaction means number of degree of freedom in constraint system. Okay, so looking into this, there are 4. There are 4. 4 means 4 DOF in constraint system. So remaining is 2. Remaining is 2. So in total, there are 6. 2 plus 4. 2 in unconstrained, 4 in constraint. Okay. Okay, again. Okay, this is just for the first time. You have to, it is look like quite difficult to understand it for first time. Don't worry. Later on, when you have understand about the stiffness method, actually identifying degree of freedom in terms of constraint and constraint, constraint and unconstraint is actually very simple step. Okay. Okay, we do another one. Okay, I repeat the truss again. Okay, this is the truss. This truss has 2 pin here. Okay, this truss has 2 pin. There are 3 nodes. Node number 1, node number 2, node number 3. Okay, so there are 3 node number, and 3 node number means, okay, there are combination of element. So element, we name, we put element name, element number, element joining to nodes. Element we write in the box. Okay, element 1 joining node number 2 and node number 3. Element 1 joining node number 2 and node number 3. And element number 2 joining node number 2 and node number 1. There is no rules. You can also write like this. It's up to you. Okay, there is no rule in numbering nodes, in numbering element. There is no rule. You can also write this 1, 2, 3 if you like. Doesn't matter. Okay, 1, 2, 3. There are 3 nodes. Now I have changed the node number. I put the previous node number 3 as node number 1. Doesn't matter. We can label anywhere. Okay, and then we have to label also element number. Just join 2 nodes become 1 element. Joining 2 nodes become 1 element. We can label 1 and 2 like this, or the other way around. Okay, so we have 2 elements. So the first thing to do before we start analyze structure using stiffness method, we have to put node number. This is the first thing to do. Okay, if you get the question without any numbering, you have to put node number. Normally you will get with node number. Okay, but if you have structure without numbering at all, so you have to put, first thing is node number. Okay, second thing that we have to put into the diagram, second thing is element number. Element number. So from this there are 2 elements. We have element 1 joining node number 2 and node number 3. Element 1 joining node number 2 and node number 3. And we have element 2 joining node number 2 and node number 1. Okay, we can label as you like. Doesn't matter. There is no rule. Just label. Okay, just label. Element number. Element number. Okay, number 3. We have to label degree of freedom. In the diagram, we have to label degree of freedom. Also in number, degree of freedom. And look at the node number. Remember, this is TRUSSS. TRUSSS has 2 degree of freedom in X and Y component. This direction, it is compulsory. This X, Y, okay, will be put at each node. Node number 1 has X and Y. Node number 2 has X and Y. Node number 3 has X and Y. Okay, so in total, degree of freedom is 3 times 2. Degree of freedom for this TRUSSS is 3 times 2. 3 times 2, 6. There are 6 degree of freedom. However, this 6 degree of freedom, we have to divide into 2. Unconstrained and constrained. Unconstrained and constrained. So we have to identify unconstrained and constrained. Unconstrained and constrained. Okay, this is under degree of freedom. Unconstrained degree of freedom, constrained degree of freedom. Okay, in total there are 6. Okay, how to identify unconstrained? We cannot get clear picture from unconstrained. We cannot label, we cannot identify number of unconstrained first. We will identify number of constrained degree of freedom from support, because constraint refers to support. So just look at the diagram, look at the support. Okay, look at the support. There are 2 pin support. 2 pin support means there are 4 unknown reaction. 2 pin support means there are 4 unknown reaction. 2 pin support means there are 4 unknown reaction. So we have to put 4 here. 4. 2 pin support means there are 4 unknown reaction. Where to put? Constraint system. Where to put? Constraint system. So after putting 4 here, so we have remaining 2, because in total there are 6 degree of freedom. There are 6 degree of freedom. So we have to put another 2. So where is this 2? So this 2 is 2 degree of freedom in unconstrained system. Okay, 2 and 4. Total is 6 degree of freedom. So we have to divide into these 2, unconstrained and constrained. Okay, so what is the meaning of constraint? Just imagine support. Just imagine constraint DOF. Just imagine unknown reaction. Constraint degree of freedom. Just imagine reaction at the support. Constraint degree of freedom. Okay, constraint degree of freedom. And we have to label degree of this degree of freedom. We have to label degree of freedom 6 into the diagram. We have to label. We have to label these 2. We have to label these 2, and we have to label these 2. There are 6. 2 per node. 2 degree of freedom per node. And we have to label. We have to label according to unconstrained and constrained, unconstrained and constrained system. Okay, so looking back into this, the degree of freedom, we have unconstrained and constrained. Okay, the best way to understand this is by separating this into 2, means that we will sketch separately before we combine into 1. We will sketch the degree of freedom in unconstrained system and then constrained system. We draw it separately. We label it separately before we combine into 1. So we have to sketch 1 for unconstrained and 1 for constrained. one for unconstrained, and one for constrained. Okay, so just cash, doesn't matter. Just like this also acceptable, because the focus now is to put the x and y. Okay, whenever we draw, we start with unconstrained, constrained. The diagram, okay, the left diagram refers to, this is unconstrained. This is unconstrained. Degree of freedom. Okay, unconstrained, degree of freedom. And constrained, degree of freedom. We draw it separately. Unconstrained degree of freedom, constrained degree of freedom. Just sketch the element line like this. Okay, element line like this. And from this, okay, degree of freedom in constraint, there are 4. Okay, in constraint there are 4, so we have to put 4, 2 at node number 1, and 2 at node number 3. Okay, so we put, where is the location of pin support? Where is the location of pin support? It is for constraint system. Where is the location of pin support? This is pin support, this is pin support. Okay, pin support means that we have to put degree of freedom 2 and 2. That what is mean. Okay. Okay, this mean degree of freedom in constraint system in x and y direction. So we put 4 here. 4 degree of freedom. We put 4 degree of freedom at node number 1 and at node number 3. At pin support, we have to put 4, because there are 4 unknown reaction. And 4 unknown reaction means 4 degree of freedom in constraint system. 4 degree of freedom in constraint system. Okay, 4 degree of freedom in constraint system. And we have to follow the sign convention, x and y. Okay, we cannot change the direction. Okay, and after this, we have to complete all 6. And the remaining 2, okay, only 4 DOF in constraint, remaining 2 will be put in unconstrained system. The remaining 2 is located at unconstrained system to complete all 6. So this is another 2. Okay, another 2. If 4 belong to 4 unknown reaction, 4 refers to 4 unknown reaction in constraint system. Okay, so remaining we have to put under unconstrained system, so that when we combine we get all 6 degree of freedom. Okay, so whenever I draw, okay, these two separately, we are between unconstrained and constrained, I start with unconstrained, even though labeling start from constraint. But when I draw, so I will draw like this, unconstrained first, then only constraint. Okay, why? Because we will label 1, start from unconstrained. So now we will label this degree of freedom from 1 to 6. From 1 to 6, we label as 1, 2. 1, 2, X, Y. Okay, please label X first, then Y. When it has complete degree of freedom, like this, at one node, so put 1 and 2. 1, 2, X, Y. 1, 2. Then only we label constraint, followed by 3, 4, 5, 6. Okay, 1, 2, 1, 2, 3, 4, 5, 6. 1, 2. In unconstrained system, 3, 4, 5, 6. Okay, so in total now there are 6 degrees of freedom. So this 6 degree of freedom we will put into this diagram. Okay, so 1 and 2, 1 and 2, 3, 4, 3, 4, 5, 6. Okay, so there are 3 types of numbering here. 3 types of numbering here. Okay, we have number in circle representing node number. Number in circle representing node number. Okay. Number 2, we have element number. Element number, and element number is number in box. Element number is number in box. Okay, and we have another one called as degree of freedom. We need to label also. Okay, label also from 1 to 6 because there are in total 6 degree of freedom. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is how we numbering. Okay, this is how we numbering. We numbering the degree of freedom according to unconstrained and constrained degree of freedom. Okay, going back to this, we have to understand the characteristic of each system. We have unconstrained degree of freedom and constrained degree of freedom. Okay, constraint first. Constraint first because constraint is support. Constraint, what is the first characteristic? Constraint is support. Okay, constraint is support, pin support or roller support. Okay, there is no fixed support in TRUSS. There is no fixed support in TRUSS. There is no moment in TRUSS. That is why the sign convention XY, we only have X and Y. We don't have X, Y, Z, Z. We don't have X, Y, and Z, Z. Okay, Z refers to moment, Z refers to rotation. We don't have moment, we don't have rotation in TRUSS. Okay, we have horizontal displacement, we have vertical displacement. Horizontal displacement, TRUSS at node has horizontal displacement, vertical displacement, but there is no rotation. There is no rotation in TRUSS. That is why we only need to count 2 degree of freedom. We don't count rotation. There is no rotation. There is no fixed support. There is no moment. So TRUSS has horizontal force, vertical force only. Horizontal force, vertical force. That is why we count as 2. We do not include moment in TRUSS. So originally we have 3. X, Y, and Z. X, Y, and Z. This X, Y, and Z component, we can look into it as forces and displacement. Forces, X is horizontal force, Y is vertical force in terms of forces, the degree of freedom. But in TRUSS, we don't have moment. That is why we only count X and Y component. Okay, in terms of displacement, deflection, displacement in TRUSS, we will only have horizontal displacement, vertical displacement, vertical displacement, and we don't have to count rotation because there is no rotation in TRUSS. That is why we have 2 degree of freedom, X and Y component. Okay, X and Y component, we must we must look into this X and Y in terms of forces and in terms of displacement. Okay. So under constraint means support. Constraint means support. So support. Imagine support. Okay, at support there is no movement. At support there is no movement. So here we have 3, 4, 5, 6. 3, 4, 5, 6. Okay, 3, 4, 5, 6. And remember what I mentioned just now, degree of freedom, X and Y, this X and Y. Okay, if it is displacement, okay, displacement in X means horizontal displacement. Displacement in X means horizontal displacement. And displacement in Y is vertical displacement or deflection. Vertical displacement. And we don't have rotation. That's why we count as 2. And this is displacement. And in terms of forces, we have Q. Q in X direction, Q in X component means that it is horizontal force. And Q in Y component refers to vertical force. Okay, why we have Q and D? Because of the stiffness equation. Q is equal to KD is stiffness equation. Q is equal to KD is stiffness equation. Q is equal to KD. K is stiffness matrix. We will produce the stiffness matrix. Okay, K stiffness matrix. The stiffness in matrix. Written in matrix. Okay, so Q also we have to write in matrix. D also we have to write in matrix. So this Q is nodal forces, K is stiffness matrix, the structure stiffness matrix, and D is nodal displacement. Okay, so degree of freedom we always refer to Q and D. Okay, by understanding this, okay, refer back to this constraint system. We have labeled as 3, 4, 5, 6. We have labeled this as 3, 4, 5, 6. So this 3, 4, 5, 6. Okay, support, what does it mean? Support means no displacement. Support, there is no movement. Means that D equal to 0. There is no movement. D is equal to 0. Which D? D3, D4, D5, D6. Which D? D3, D4, D5, D6. Means that displacement, horizontal displacement at node 1. Horizontal displacement at node 3. Okay, there is no movement. Okay, there are four displacement here, and all these 4 displacement will be equal to 0 because it is support. At support, no displacement. So D is equal to 0 here refers to D3, D4, D5, D6, and this D, all D, D3, D4, D5, D6 are 0 value. Because it is support. Okay, what are the other characteristic of this? Okay, Q is unknown reaction. We name it as QU. QU. QU, unknown reaction. This is unknown reaction. How many unknown reaction? We have 4 unknown reaction. How many unknown reaction? We have 4 unknown reaction. What is the level of unknown reaction? What is the level of unknown reaction? Okay, what is the level of unknown reaction? Q3, Q4, Q5, Q6. Okay, Q3, Q4, Q5, Q6. Okay, so what I want to, okay, we call this as unknown. So D0 means D0 means known displacement, known displacement, and known lawan dia unknown. Okay, known lawan dia unknown. Okay, known, the opposite of known is unknown. Known displacement, unknown reaction. D and Q ni dia akan always opposite condition. So at every position, at every notes, we have to look into it in terms of D and in terms of Q, and the characteristic between D and Q is always opposite. If D is known, Q is unknown. D is known, in this case D is 0, Q is unknown. So this unknown reaction will be determined. This unknown reaction will be determined. Q. Okay, Q. And this Q, normally in textbook, the label used for constraint system is QU, Q unknown, Q unknown, Q unknown. And the label used in the textbook, D for non-displacement is DK, 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 known, DK, DK and QU, DK and QU. Okay, now we compare between unconstrained and constrained. Unconstrained and constrained. We compare between this. Okay, because looking into this, the condition will always opposite. Will always opposite. Opposite. Okay. So in unconstrained system, D is unknown. In unconstrained, if in constrained, Q is unknown. In unconstrained, D is unknown. Unknown displacement. Unknown displacement. DU. 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 Unknown displacement, there are 2. D1 and D2. D1 and D2. D1 and D2. DU refers to unknown displacement. D1 and D2. D1 and D2. Okay? And the opposite. Unknown displacement, known forces. Known forces. Unknown displacement, unknown D means the other one will be known. Known Q. Known Q. Known Q. Known Q is QK. Okay, known Q is QK. It is opposite between these two. Okay, okay. Logically, okay. If we have this truss, pin here, and there is forces 100 kilonewton. Logically, 100 kilonewton. Okay, this is support. No movement, displacement 0, displacement 0. Because of the support, what happened to this? There is no support. There is no support means this point will move, right? It will move. Okay, that is the actual condition. If we compare unconstrained and constrained. Okay, unconstrained and constrained. So that's what it means. So if we label this as 1 and 2 here, 1 and 2, 3 and 4 here, and 5 and 6 here. Okay. 1, 2, 3, 4, 5, 6. 3, 4, 5, 6 is constraint. Unconstrained, lawan dia constraint. So the condition is always opposite. Okay, so we can write displacement, 6 value of displacement from 1, 2, 3, 4, 5, 6. And we can also have to write Q in matrix form. There are 6 value because 6 degree of freedom, 3, 4, 5, 6. Okay, so there are 6 degree of freedom. Degree of freedom, okay, degree of freedom, we have to look into it in terms of D and in terms of Q. In terms of D and in terms of Q. Okay, so the boundary between unconstrained and constrained is here, the boundary. Okay, 3, 4, 5, 6. 3, 4, 5, 6 is constrained. Unconstrained is 1, 2. Unconstrained is 1, 2. Okay, so for displacement in constraint system at position 3, 4, 5, 6, because of the support, all these are 0. Displacement at support, we label as 3, 4, 5, 6. We label as 3, 4, 5, 6. Okay, all 0. All 0. All 0. And in opposite condition, Q, 3, 4, 5, 6 are the reaction at the support, and this is the unknown reaction. And we have to label as like this, as symbol like this, 4, 5, 6. Q3, Q4, Q5, Q6 are the unknown reaction, unknown value. So we just put like this, Q3, Q4, Q5, Q6. These are the 4 unknown reactions that we will determine at the end of analysis. At the end of analysis. The same position with D. The same position with D. 3, 4, 5, 6. At support, no movement, no horizontal movement, no horizontal displacement. No horizontal movement, no horizontal displacement. No vertical displacement. Okay, and in Q, 3, 4, 5, 6 are reaction at the support, and that is what we are going to calculate at the end of analysis. Okay, so in the other way round, at 1 and 2 refers to unconstrained. So 0 means known, known versus unknown, known versus unknown. Known versus unknown. This all 0, known value. So known versus unknown. So for 1 and 2, because of the movement due to 100 kilonewton, this point can move, and we do not know the value. So that is refers to D1 and D2. D1 and D2, this is unknown displacement. Unknown displacement D1 and D2. Unknown displacement D1 and D2. Okay, this is the condition, opposite. D1 and D2, opposite like this, right? Both of these are unknown. Unknown displacement in unconstrained system, unknown reaction in constrained system. Okay, and for Q value 1 and 2, we have to refer to the diagram. Q1 and Q2. We have position 1, position 2, we have to put the value of Q. Because 3, 4, 5, 6 are the unknown, and unknown versus known means that 1 and 2, we have put value, known value. So how to get the value? Look into the diagram. 1 and 2. 1 is horizontal force. 2 is vertical force. Okay, at position 1, DOF is position. At position 1, there is no horizontal force given in the question. The value is 0. The value is 0. And look at 2. 2 refers to vertical force. 2 refers to vertical force. And there is a vertical force. It is 100 kilonewton. 100 kilonewton, okay, which is opposite with sign convention between 2, 1, 2, 2, between 2 and 100, the direction is opposite. The direction is opposite, so we put as negative 100. Negative 100. So these two refers to degree of freedom. Okay, degree of freedom in terms of D and in terms of Q. In terms of D and in terms of Q. Okay, so these things is very, very important. This thing is very, very important. So we have to understand about the term unconstrained degree of freedom and constrained degree of freedom. And degree of freedom, we have to translate into these two metrics. And nodal forces written in matrix and nodal forces written in matrix. Okay, that is for this TRUSS. That is for this TRUSS. Okay, so let's do another example of TRUSS. Okay, before we end session, we have another 30 minutes. Okay, again. Okay, we have to understand more. We have to understand more about degree of freedom, unconstrained and constrained. Okay, let's have this. Okay, let's have this. Okay, let's have this. Okay, doesn't matter if this is determinate structure, doesn't matter. Just to get the concept first. Okay, so let's say we have force 150 kilonewton. 150 kilonewton. Okay, thrust, this thrust must have node number, element number, and degree of freedom. Degree of freedom. Node number. So we just need to label. Node number 1, node number 1, node number 2, node number 3. Remember, node number we have to label in the circle. Okay. This truss has 3 elements. Element, okay, we just put the element number. Element number. Okay, 3. Okay, there is no rules, just put 1, 2, 3. Means that here there are element number 1 joining node number 1 and node number 2, element number 2 joining node number 2 and node number 3, and element number 3 joining node number 1 and node number 3. Okay. Now is degree of freedom. Degree of freedom, there are 3 nodes, 3 times 2. 3 times 2. In total, there are 6 DOF. 6 DOF. 6 DOF. Okay. Means that there are 6 DOF. 2 per node. 2, 2, and 2. 2 per node. 2 at node number 1, 2 at node number 2, 2 at node number 3. So in total, there are 6 degrees of freedom. Now, we have to label this according to unconstrained and constrained degree of freedom. And constraint refers to reaction at the support. Looking at the support, there are 3 unknown reactions. There are 3 unknown reactions. Pin at 1, roller at 3. There are 3 unknown reactions. Okay, so in order to numbering this correctly, we draw this diagram. We sketch the diagram. Okay, we sketch the diagram again, just for the purpose of labeling. Okay, this is unconstrained, constraint, unconstrained, constraint. Okay, looking at note number 1, there are two degree of freedom. There are 2 degree of freedom. 2. So we have to put 2 here. 2. Because this is the point where the pin is located. 2. X and Y. X and Y. We have to use this sign convention. We cannot change. Okay. Note number 3, we have roller. We have roller. Roller, normally roller, we draw just like one only, right? Okay, Y, in Y direction. Not in X, but in Y direction. Okay, so this representing reaction at note number 3. If this is C, this is CY. If note number 3 is C, it is CY. So CY, how we draw the free body diagram for CY? Like this. Okay, CY. Means that there are three degree of freedom in constraint system. Like this. And we have to complete remaining. We have to complete remaining 3 because 3 have been put under constraint system. We have remaining 3. Just complete 2 each node. 2 per node. Okay, we have to complete node number 3, we have to put X, the sign convention for X. So here is another 1. Okay, because we only put 1 in constraint, another 1 we will be put in unconstrained. Okay, and another 2. Okay, so now there are 3 degree of freedom in unconstrained and 3 degree of freedom in constraint. 3 and 3. 3 and 3. Now we have to label. When we label, always remember, when we label unconstrained first. We label unconstrained first. So we label 1, 2. 1, 2. 3. 1, 2, 3. 1, 2, 3. Means that 1, 2, 3, D1, D2, D3, Q1, Q2, Q3. Okay, then followed by 4, 5, 6. 4, 5, 6. What does it mean? What does it mean? Okay, what does it mean? Okay, in constraint, displacement 0. Okay, displacement 0. This is unknown displacement, du. Okay, du, unknown displacement. Okay, so means that D3, not D3, D4. Means that D4 is 0, D5 is 0, D6 is 0. Okay, D4, D5, D6, 0. D1, D2, D3, D1, D2, D3. Okay, all this, okay, D4, D5, D6 is known displacement. Known displacement versus unknown displacement. Unknown displacement. Unknown displacement. So, if we want to write D1 until D6 in matrix form, D in matrix, we have 6. We have 6. 1, 2, 3, 4, 5, 6. Okay? 4, 5, 6. 0, 0, 0. 4, 5, 6. 0, 0, 0. That is for known value. 1, 2, 3. 1 to 3 refers to unknown, so we remain as symbol. D1, D2, D3. D1, D2, D3. So this is how we write the nodal forces. D1, D2, D3, unknown displacement. D4, D5, D6, known displacement we get from support. Okay, the other way round is Q. Q. For Q, the label 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 4, 5, 6 refers to 4, 5, 6 refers to unknown reaction. 4, 5, 6 unknown reaction. 4, 5, 6. In constraint system, known displacement, unknown reaction. Non-displacement, unknown reaction. Non-displacement, unknown reaction. Unknown reaction. Unknown reaction, the symbol is QU. QU. U refers to the label 4, 5, 6. Okay, the opposite. So here we put Q for Q5, Q6. Always opposite between this, because this is the boundary between unconstrained and constrained. Okay, like this. Okay, opposite condition. This just to refer to the opposite condition. So unknown displacement, we determine in unconstrained system. That's what I mean. Okay, by put the green line. Unknown displacement is located in unconstrained system, and unknown reaction is located in constrained system. Okay, so it is always opposite. It is always opposite condition: unconstrained and constrained. Known and unknown. So for Q1, Q2, and Q3, because it must be opposite with 4, 5, 6, because 4, 5, 6 is constrained. 1, 2, 3 is unconstrained, and the condition is always opposite. So 1, 2, 3, we have to put value. It cannot be symbol. We have to put value. Q1, Q2, Q3. Q1, Q2, Q3. Looking into the diagram, 1, 2, 3. 1, 2, 3. Q1, Q2, Q3. Q1, horizontal force. Q2, vertical force. Q3, horizontal force. Okay, so what is Q1? Refers to the main diagram, Q1. Okay, Q1 at node number 2, that is 50 kilonewton. Same direction, so it is 50. Q1 is 50. Q1 is 50. It is 50. 50. Okay? Now, 2. Position 2. Okay, looking into this, 2 is vertical force. Q is vertical force. Look into the diagram. Okay, 100 kilonewton, opposite. 100 kilonewton downward, and it is opposite with sign convention. It is negative 100. Negative 100. So it is negative 100. Okay? And 3, position number 3. Look back into this. Position number 3. Okay, position number 3. Horizontal force at node number 3. Horizontal force at node number 3. There is no horizontal force at node 3. There is no horizontal force. Just look at into this. This is 3, 4. This is 3 and 4. Q3. Q3. Only if the horizontal force is given in the question, then it has value. Now, the horizontal force is not subjected here. So, the value is 0. So, inside the matrix, the value is 0 unless the value is given in the diagram. Okay, so this is the degree of freedom. So by understanding degree of freedom, according to unconstrained and constrained system, we have to be able to establish what we call as nodal forces and nodal displacement written in matrix. Okay, the degree of freedom, it has 6 because of 3 nodes, 3 times 2. So D will be D1 until D6. Q will be Q1 until Q6. So between this Q and D, okay, of course, there are, due to unconstrained and constrained system, the condition is opposite. Okay, always remember that we determine unknown displacement. We determine unknown displacement in unconstrained system. We determine unknown displacement. There will be movement because there will be movement at 1 and 2 and 3. Okay, because of the loading that is subjected into the joint. Okay, and at support there will be reaction. At support there will be reaction. No displacement at support. That is why we get 0 at 4, 5, 6. So known versus unknown. Known versus unknown. Known 0, 0, 0, 4, 5, 6. Known versus unknown Q4, Q5, Q6. So using stiffness method, we will apply Q is equal to KD. It is called as this force displacement equation. Force displacement equation. Force is Q, D is displacement, force displacement equation. This is also the stiffness equation. Using stiffness equation, we will solve number 1, unknown displacement, D1, D2, D3. D1, D2, D3. Then we will solve unknown reaction, Q4, Q5, Q6. Okay, using stiffness method, by solving stiffness equation, we will solve displacement first. And after that, we use the displacement that we get to calculate reaction at the support. Okay, that is why we have to label D start from D. The unknown displacement will be determined first. That is why we label D. 1 start from D, followed by Q. Okay, unconstrained we label first, followed by constrained, because we will determine D1, D2, and D3 first. D1, D2, and D3 first. Okay, so that is okay. That is unconstrained degree of freedom and constrained degree of freedom. We have to understand the term very well. Okay, we should be able to translate it into the diagram. Okay, we have to label the degree of freedom according to unconstrained and constrained system, because at the end of analysis, we will determine unknown displacement in unconstrained system, and we will determine unknown reaction in constrained system. Okay. Okay. I will continue to discuss about the stiffness matrix, the element stiffness matrix, and the structure stiffness matrix in the next session. Okay, so I hope you understand about degree of freedom, because that is very very important. Degree of freedom. Okay, as I put into the poster for today's session, understanding degree of freedom, then only we can move to stiffness matrix, the element stiffness matrix and the structure stiffness matrix. Okay, so uh, have understanding about degree of freedom first, about the unconstrained system, about the constrained system. Okay, very well. Okay, read the notes in the textbook. Okay, find another sources of material about to understand more about the definition of unconstrained and constrained degree of freedom. Okay, and you should be able to translate all the information in the diagram in D and Q, nodal forces and nodal displacement in matrix form, like what I have shown to you just now. And after that, and only after that, we will continue to formulate what we call as element stiffness matrix and structure stiffness matrix in the global coordinate system. Because this is K, this is K. Remember, Q is equal to KD. Q is equal to KD. We have understand about Q, understand about D. Okay, and then we will formulate or produce the structure stiffness matrix K, and then we will combine in one equation. Stiffness equation, force displacement equation, we will write in matrix form, and we will solve for displacement and reaction at the support by solving the stiffness equation. Okay, so we will continue the next session. Will be the online session as well to continue this. I will let you know when is the next session. Okay, to cover this. Okay, stiffness, element stiffness matrix as well as structure stiffness matrix. Okay, so that's all for this session. We will meet again in the next session. Thank you very much. Okay, Assalamualaikum warahmatullahi wabarakatuh.